All right, let's jump right in. Today, we're going to pull back the curtain on the invisible engine that powers so much of our world. We're talking about the secret sauce behind AI, machine learning, and so many of the tools you use every single day. We're talking about statistical learning.
You know, the great Yogi Berra really hit the nail on the head with this one. For all of human history, trying to figure out what's coming next has been, well, a huge challenge. But what if we could use data to get a clearer picture, to actually get a little bit better at predicting the future? That's really the core mission here.
And that mission has never been more important, because right now we are practically swimming in data. It's being generated every second from every corner of the globe. The problem isn't getting information anymore, it's figuring out what to do with it all. And that's the billion-dollar question, isn't it? It doesn't matter if you're in business or biology or computer science. Everyone is trying to do the same thing. Find the real patterns hidden in all that noise. How do we take just raw numbers and turn them into actual insights that can help us make better decisions?
Well, the answer lies in a really powerful set of tools designed for this exact problem. So let's meet the star of the show, statistical learning.
So what is it, really? At its heart, you can think of statistical learning as this huge collection of methods we use to build models from data. And these models are the key. They let us do one of two things: either predict what's going to happen or understand why things are happening. This is really the bedrock of what we now call data science and machine learning.
Now, I love this philosophy for how to approach these tools. Think of it like driving a car. On one hand, you don't need to be a mechanic who can build an engine from the ground up just to drive to the grocery store. But, on the other hand, you can't just treat the car like a magic black box either. You got to know the rules of the road, right? It's the same here. You need to understand the basic ideas and trade-offs. The most accurate models can sometimes be the hardest to understand, while the simpler ones are much easier to explain. It's all about picking the right tool for the job.
So when we build these models, what are we really trying to do? Well, it almost always boils down to one of two big missions: prediction or inference. Let's use a real estate example to make this super clear. Prediction is all about the what. You feed the model the size of a house, its location, how old it is, and it spits out a price. The goal is just to get the number right. Is this house a good deal? But inference is about the why. It's about understanding the relationships. Which things actually drive the price up? How much is that river view really worth? See the difference? One predicts, the other explains.
Okay, that's enough theory. Let's see how this stuff actually works out in the wild. We'll start with a classic business problem, and then we'll look at something, well, a little more mind-blowing.
This is a fantastic, real-world example. So we've got data from 200 different markets. We know how much was spent on TV, radio, and newspaper ads, and we know what the sales were. The goal is simple. Can we build a model that predicts sales based on how we spend our advertising dollars? It's a perfect, concrete case of statistical learning at work.
Predicting sales from budgets, that seems pretty straightforward. The numbers are clean, the relationships are probably pretty direct. But what happens when your data isn't a neat little number in a spreadsheet? What happens when it's something way more complex, like, say, the pixels in a photograph? Take a look at this. You and I see two flamingos. We don't even have to think about it. It's instant. But to a computer, this is just a massive grid of numbers, millions of them, that represent color and brightness. So, how in the world do you teach a machine to look at that grid of numbers and learn to see a flamingo? That's a huge leap in complexity.
And here is the absolutely incredible result. A modern deep learning model, this one's called ResNet 50, it's been trained on millions of images, and it can look at that chaotic grid of pixels and say with 83% certainty, yep, that's a flamingo. That's not just recognizing a pattern anymore. That is a form of machine perception, and it's all made possible by statistical learning. It's amazing.
So, what does all this incredible power mean for our future? This ability for machines to learn from data is, and I'm not exaggerating, completely reshaping our world.
And it's really important to realize this didn't just happen overnight. All the deep learning breakthroughs that you hear about today, they're built on ideas like neural networks that go all the way back to the 1980s. So what changed? Why now? Well, it's really two things. We now have absolutely massive amounts of data, and we have the sheer computing power to process it all. It's like the ideas were just waiting for the technology to catch up.
And believe me, this isn't some abstract science fiction stuff. This toolkit is the engine running under the hood of self-driving cars. It's helping doctors find diseases earlier and with more accuracy. And it's behind every recommendation algorithm that suggests what you should watch or read or buy next. It is already totally woven into our daily lives.
So, this is where we'll leave it.
We have built this incredibly powerful set of tools to understand and predict the world around us. The question is no longer just, can we do it? The real question now is, what should we do with it? What are the next huge, important problems that we're going to choose to solve with the power of statistical learning? That's the really exciting part, and it's something for all of us to think about. Thanks for tuning in.